Hello everyone, welcome back to the another class of fundamentals of particle and fluid solid processing. In continuation with our last class, as I mentioned, we will be again dealing with another problem relating to the concept of fluid flow through granular and packed bed of particles, especially focusing on how Argan equation can help us in achieving some of the design parameters, or in other way what is the applicability or what is the utility of Argan equation that we have now we saw in last couple of classes. So, the problem here is that a solution of density 1100 kg per meter cube and viscosity 2 into 10 to the power minus 3 Pascal second is flowing under gravity at a rate of 0.24 kg per second through a bed of catalyst particles. The bed diameter is 0.2 meter and the depth is 0.5 meter. The catalyst particles are cylindrical with a diameter of 1 millimeter and length 2 millimeter. Okay. They are packed to give a voidage of 0.3. So, you have to calculate the depth of liquid above the top of the bed. So, which means say we have a bed of particles and fluid is flowing downward. In this case, okay, it is falling under gravity at a rate of 0.24 kg per second through a bed of solid catalyst. The bed diameter is mentioned, the depth of the bed is given. The particles are cylindrical in nature, so that means the particles are of in this shape with a diameter dp is known and length, if I say small l, that is also known. So, which means particle volume and the particle surface area can be calculated, and they are packed. These particles are packed in here with a voidage of 0.3, which is the void space through which the fluid can flow. Now, quite naturally, what will happen at steady state, since there is a resistance due to this bed, some amount of, if this is my bed, some amount of liquid water, okay, or let us say here a solution at a steady state will be there. So, we have to calculate this depth of the liquid above the bed. Okay. What is this thickness or the depth of this liquid pool that will be accumulated at the top of the bed? Okay. So, how do we do that? But first of all, realize that this is a problem regarding the flow through packed bed of particles. Here the particles are cylindrical in nature, solution of the fluid density, viscosity, mass flow rate, which can be converted to volumetric flow rate, which further can be converted to the superficial velocity if the bed cross section is known, that is given. Okay. The bed cross section is also given, which means the superficial velocity can be calculated. The bed diameter is given as this. the bed depth is mentioned, okay, the voidage, everything is known. So, first of all, what is the pressure drop across this bed, okay, and then we go for this next calculation, and we will see that how we calculate this depth of liquid field or the depth of liquid pool above the top of the bed or above the on top of this bed, okay. So, first of all, we calculate what is the superficial velocity. Here this is the mass flow rate, okay. This mass flow rate is first of all divided by the density of the solution, which gives the volumetric flow rate, which is 1100. This is the density mentioned, divided by pi d square by 4, which is the cross section of the bed. Fine. This provides us the superficial velocity of this problem. Now, the particles are not spherical here, the particles are cylindrical in nature, which means the volume of one cylindrical particle is this millimeter cube, okay, because for a cylinder you know how to calculate the volume, you also know what is the surface area of one particle, okay. So, the surface to volume ratio is 2.55 pi divided by pi by 2 millimeter square by millimeter cube. So, this gives the surface to volume ratio. Now, since this is the irregular shaped particle, or let us say not spherical, we basically have to find out what is the surface volume mean diameter. So, which means the equating the surface to volume value, this ratio, okay, with the same surface to volume ratio of a sphere, and find out that what is the diameter of such sphere that has this same surface to volume ratio. Now, surface to volume ratio for a spherical object is 6 by d or 6 by xv, isn't it? Then what we do from this relation, we get a surface volume mean diameter of these particles are as 1.22 millimeter, 1.2 millimeter, because in the Argon equation, which is actually derived or actually been proposed for the mono-sized spherical particles. If you remember during that class, I mentioned that Argon equation was strictly valid for the mono-sized spherical particles, okay, the single phase flow it's happening. So, now to satisfy those criteria, we had to calculate what is the mean diameter, and this mean here, because here in Argon equation contact area, the surface to volume ratio is of main importance. So, we find what is the surface volume mean diameter here, and this is how we did it, because here for a single cylindrical particle, its diameter and length or the required dimensions were mentioned. We convert or we calculate that with the surface to volume ratio and find out the value, and then that equate with the surface volume ratio of a unknown diameter of a sphere, that is 6 by d or 6 by xv here, and then we find out what is the xv in argon equation that is to be put. Okay. So, first of all we got the superficial velocity, we have got the mean diameter in terms of surface volume diameter. Okay. So, we can calculate now what is the Reynolds number, because this helps us to utilize the effective part or the most dominant part of the argon equation, or in fact you can choose between the Koenig-Ehrmann or the Bark-Palmer part. So, here now if we replace these values, that is the u we have just now calculated, the density, okay, and xsv which we just have calculated, that divided by the viscosity multiplied by 1 minus epsilon. This gives the particle Reynolds number as 6.5, which is less than 10, and we can consider that it is definitely a laminar flow. Fine. So, with all the information, since we did not know initially whether the problem is laminar or turbulent, to use the appropriate expression for the del P, we can calculate this Reynolds number and then use the appropriate part of the argon equation, which is valid for a wide range of operation. So, here this is the viscous part. Okay. Now, here I believe all the parameters are now known to you, that is mu is known, or the fluid viscosity, fluid density, particle diameter or the mean diameter here because the particles are cylindrical in nature, the epsilon or the voidage, and the height of the bed or the bed depth. If we replace this all the numerical values in this expression, we get del P per unit length or the pressure drop per unit length or the pressure gradient as 26240 Pascal per meter. Clear? So, is this the pressure gradient that will happen in this problem or this kind of flow situation? But our question is that how much liquid depth will be there, okay, on top of the bed. So, the scenario is something like this that I mentioned, that we have the bed and on top of this there will be the liquid pool. So, if we say that this is the height of the liquid pool, okay, and this is the point 2, this is the point 1, fine. We convert, we apply this mechanical energy balance now, okay, for between or in between these 2 points. That is point 2 and point 1, assuming let us say the pressure, okay, P1 and P2 are identical, as well as U1 and U2 are equal. Okay. That leaves the head loss as this value. So, we apply the mechanical energy balance between point 1 and point 2 and find out that what is the head loss, the frictional head loss. Or in other words, you can see that this is minus del P, okay, which is the pressure drop. So, this value multiplied by 0.5, which is 13,120, divided by rho g, that is the frictional head loss, which is equals to Z2 minus Z1. The height of the bed is known. So, the depth of liquid above the bed is 0.716 meter, because if this is the total height and in between that, so this is this Z2 minus Z1, this is 1.2. So, this is my Z2 minus Z1, which is 1.216. In between we have the known bed depth of 0.5. So, this is our height of 0.716. So, to apply the mechanical energy balance, we had to know the frictional head loss, which came from our applied Argan equation, or the first part of the Argan equation, that is the del P, that is the total head loss between 0.1 and 0.2. Okay. Assuming at steady state case these two are equal, as well as the pressures are equal at these 2 points, these pressures, then the height difference is what? The head loss, and that height difference includes the height of the bed, which means the depth of liquid on top of the bed is also known. I hope this problem is clear to you. Okay. So, we move on to another concept which we have already seen its form, but let me again state you that there is, when particularly in a very fine material and in petroleum industry, let us say the soil mechanics and etc., similar to that, when there is a flow through this kind of we say porous medium, okay, the soil, you can understand that this is the porous media, the filter cake or the filter medium, that is a porous media, that is not particularly of any kind of fine material, okay, but any membrane or something like that, that also can be of such kind of very fine granular material. And then when there is flow through such granular material or very fine materials, okay, the relation between this pressure drop and its flow rate, okay, at the beginning of the slide or this section I mentioned that initially it was Darcy who saw this relation or who proposed this relation, that it is the pressure drop or when he experimented with the flow of water through a bed of sands of various thicknesses, he saw that the average velocity is proportional to the driving pressure, and inversely proportional to the thickness of the bed. Okay, which means this velocity, okay, was proportional to the driving pressure and inversely proportional to the thickness of the bed, which is the, let us say, the L here. B is the proportionality constant, A is the cross sectional area, and V is the volume of liquid that flows in time t. So, basically UC is 1 by A dV by dt. This proportionality constant B actually depends on the physical property of the bed and the fluid. Okay. So, which means when the flow is very low, or in case of low Reynolds number, we have already seen that the viscous force is actually what it dominates. Okay, the resistance mainly comes from the viscous drag. So, at low Reynolds number, in flow through granular materials of homogeneous permeability, the permeability is what? Permeability is basically analogous to the concept of conductivity. Okay, the flow, how well a flow goes through a media, that is quantified by a term called permeability. Or in other way, you can think of the inverse of permeability is the resistivity. Okay, how well or with how much easiness a flow can go through a certain media, okay, if the media is of uniform voidage or uniform resistances in all direction. Okay, in that case we say that is a homogeneous media when there is uniformity of that medium. Okay, it is uniformly exerting resistance to that flow, or inverse of resistance is the permeability, that with that much easiness or ease it can flow through that material. So, this UC, this velocity, this average velocity or the cross sectional velocity can further be related to this term, that del P, mu and L, the thickness of the bed, it is already inversely proportional, and as the viscosity of the fluid gets higher and higher, the velocity goes lower and lower because of this viscous drag. And here this coefficient B changes to K, which we call permeability coefficient. It is a measure of flowability of a fluid through a packed or granular bed or say porous medium. It quantifies that value, that the measure in which it can flow through or how easily it can flow through a packed bed or porous media. This was derived for the single phase cases. Okay, but in practice packed bed operates in multi-phase scenario. So, later several researchers have modified this relation as well to fit into the multi-phase scenario case. Okay. So, the point is, how do we know or how do we calculate permeability? Because this coefficient, if it is unknown, then there is no use of this value or this expression. Okay. So, how do we calculate permeability? Typically that is done in laboratory scale in a circular cylinder of length L and let us say cross sectional area A. If we can create a constant head difference across the bed by producing a flow rate Q, head difference I believe you understand now, because we just solved a problem that what is the head loss or the head difference when there is a pool of liquid. Now, in steady state case or a steady flow, if that is the constant head difference that you can maintain with a certain flow rate Q, then Q is basically this K A H by L, where H is that head difference, okay, L is the length of the bed, A is the cross sectional area, and Q is the flow rate. And then you get the permeability value as QL by AH. This happens in case of a constant head difference measurement case. And there is the other method called the falling head flow. In this case, what happens? You allow this head or the head loss, okay, to change with time. Initially, let us say it was H1, okay, then it became H2 after a time T2 minus, let us say initially at T1 this was H1, at T2 it became H2. This is the length of the bed, this is the cross sectional area of the bed, and this is the tube in which this is happening, this head is maintained, or a pipe. Okay. This pipe, let us say, has a cross sectional area of A, small a, and this is capital A for the bed. So, in that case we can write this balance that K A H by L, which is the flow rate in this bed, is the flow rate through that pipe, and in pipe it is changing in time. Okay. So, after this, if we simplify and integrate it over time T1 to T2 for height H1 to H2 on both the sides, we can have this expression. Here all the things can be measured experimentally, that means T1, T2, H1, H2, A, small a and length L, and then we can find out what is the permeability value. By these two methods, or let us say the simple methods, elementary methods, we can calculate or we can estimate the value of K for certain media or packed bed of particles or granular material or the fine material bed through which flow is happening. Once this permeability coefficient is known, we can apply Darcy's law to find out the pressure drop if the velocity is known, or if the velocity is known unknown, we know the pressure drop, then we can find out what is the velocity that is happening there. Okay. And in flow through packed beds, typically larger packings are used in industry scale. So, that leads to the introduction of turbulence, because as the particle diameter goes higher and higher, particle Reynolds number goes bigger, it becomes a non-laminar flow. Okay. Also, the particles in packed bed are hollow in nature, because they are meant to be provided with a higher surface area, so that there are better mass transfer with relatively small pressure gradient, which means this and also there are multi-phase cases, multi-phase flow is happening, either gas liquid or liquid liquid, something flows are in there. So, typically this Argan equation ceases to exist as it is in such cases. Okay. So, this high interfacial area between phases is what the designer looks for. Okay. The uniform liquid distribution is what is warranted in a ideal packed bed. And then there is no accurate expression for this pressure drop for the industry scale, and that is why the research is still going on to have at least the pressure drop and the liquid hold up, which means the volume fraction of the liquid that is retained in the bed per unit volume of the bed. These parameters are important in a packed bed design or the packed bed operation. So what happens in packed bed? When there is no liquid phase, let us say only gas phase is there, as the gas flow rate starts, pressure drop increases. So this is the last line. Okay. Here this dry packing means only gas flow is there, and then you introduce liquid phase. Okay. As you introduce the liquid phase, the gas phase is already there in between the particles. So liquid phase will try to penetrate those spaces. Okay, and the pressure drop increases for the particular gas phase itself. So let us say you have a constant gas flow rate, you introduce liquid phase. So initially you had this much of pressure drop, you are now getting this much of pressure drop. Okay, after you introduce this liquid phase, okay, and as you increase the gas phase, what will happen? The particle, the liquid phase, okay, with the increasing liquid phase, the interstices or the portions where gas phase already was there, the liquid phase will try to fill that space. That point we call the loading of the packed bed. From there onward, suddenly or very steeply the pressure drop rises than its initial phases. And after a certain point, at this point, okay, the whole bed is flooded with the liquid phase. That's point we call the flooding of the bed, and the pressure drop rises very steeply. As you increase the high liquid flow rate, this point reaches faster and faster or with minimum liquid gas velocity. Typically, the design of the packed bed starts with this loading point. Okay, and then let us say you flood the bed and then you drain, you take out all the liquid and the gas phase is only there. Okay, in that case, even it does not fall back to the dry packing scenario, it becomes this wet packing pressure drop, which is slightly higher than the dry packing scenario or when there was only gas phase. Okay, several researchers have proposed different relations for these different operations, okay, which is out of the scope for this course, but this is what you should know, that what are the flooding and the loading points in a packed bed. And people always try, or the designers always try to design the packed bed on these loading points and in between the flooding points. Okay. With this, I conclude this section, and we will see you in the next lecture with another section. Thank you for your attention.